So most of my days I work for the application support team in Jülich Supercomputing Center, which is, if you don't know, it's one of the largest HPC centers in Europe. So as part of that user support team, we deal with the typical issues that probably many people in this room deal with as well. We resolve our tickets, so we're the ones who get the emails about people losing their private keys or having a job crash or something doesn't work anymore and I didn't do anything, I don't know what happened. So we answer those type of questions, and some of them are very simple and are very quick to answer, and some of them are very technical and can take days or even weeks. One of the things we typically get a lot, and that we try and preempt a lot these days, is installing scientific software for people, including like tools or libraries or applications. And sometimes there are other issues that we have to deal with, like trying to help people improve their workflows, and sometimes that's not by request, it's because they cause problems for other people. And then we do training as well, so we do lots of various training things, and that's why I started getting interested in software carpentry and things like that. So going back to the particular issue of installing scientific software for people, the typical way we do this is, well, it's usually for new software, it's by user request. Somebody asks for something, we'll start looking into how we would do it. But we also get requests for, well, version upgrades or even version downgrades of particular software. People look for software configured in a particular way, different to what we already have. When we build this kind of software, we want to target it for the hardware that we actually have. And so basically, we would always typically want to build it from source, if that's possible, if we have the sources available to us. And then we would have a separate installation per cluster. Usually we're talking about the particular hardware that's involved in that cluster. And it would be highly optimized for the actual hardware that it sits on. So for the system architecture, we would have heavily tuned libraries like the MKL, for example, to math libraries, or you might have your particular MPI implementation that is preferred in that system. And then we would want to build it for the native architecture. So, well, depending on the compiler you use, that involves different flags. And also then when there are new releases of compilers or of these math libraries, for example, you would want to update those builds with these new technologies. And that's something that we also try and actively look into. And of course, regardless of the installation, you probably want to keep it around for the lifetime of the machine, because usually there's always somebody who's still using that particular piece of software from 3 or 4 years ago when the machine was initially brought online. So in each case, we would create an accompanying module file so that people can easily access the particular piece of software, that particular version of that software that they're interested in. We provide the modules, so these environment modules. We do it the same way that basically everybody else has done it since about the 90s, which is through environment modules. It's just a way to specify changes to a person's environment so they get access to a particular version of the software configured in a particular way. And any changes that you have through the module tool, it applies just to the current session. So typically you would tell people load these modules before you run your code in your job script, for example. It's a pretty easy interface. I'm sure the vast majority of people in the room have used it before. If you want to see what's available, it's module avail. If you would like to load a particular module, it's module load, and then you choose the name and the version. If you want to see what modules you have loaded at any point in time, you do a module list. And if you would like to unload the changes to your environment, it's a module unload for the software that you have loaded. You can only have one version loaded at any one time. And then if you want to start fresh from scratch, then you just do a module purge, which will just unload everything in your environment at any time. For the most part, Tickle modules of what have been most prevalent for the last few years. Probably that's a historical thing related to DISA, which was the precursor to Praise, at least in Europe. So that's like the European HPC platform. And they use Tickle modules, so they've been around for quite a long time. These days, we use, and we would recommend for other people to use LMOD. So these are Lua-based modules, and it gives a much cleaner and nicer user experience, we think. So the question that we get is, please install X software on the HPC system. And that's usually not a very easy question. It's not a very easy task to fulfill. Typically, scientific software is very error-prone, so it's very sensitive. Usually installing it involves a lot of trial and error. It can be very tedious to get it right, and very slow process sometimes. Sometimes it can take hours, days, or even weeks. It's very repetitive, so you try and repeat, and boring, of course, when it's repetitive like that. Yeah, it can take a lot of time. It can be very frustrating, and the problem that really stems from that stems from the problem of the dependency hell. So basically, you have a single piece of software, but it depends in turn on something else, which in turn depends on something else, and basically, you end up trying to support an entire software stack from the ground up, which is obviously a very difficult thing to do. And sometimes maybe that's not even worth the effort. So what are the typical issues that you have with a piece of scientific software? The problem with scientific software is that it's developed by scientists. What does that mean? I mean that they're not software developers, right? And they're not sysadmins. And they're not trained as computer scientists, and neither am I. And so they implement things with little care about how they do it. As long as it works for them, that's fine. And so in the end, that results in things like they use build tools. Even if they use build tools, they might use them in the incorrect way. They might use non-standard build tools. Their build process might be incomplete, so they might have no configuration at all. They might have no install step. They might think it's a good idea to start using interactive installation scripts where you have to answer questions all the time. It's not. Then they might have hard-coded parameters inside, so the paths to particular .h files or to compilers or libraries or anything like that. Documentation is usually a big source of a problem because sometimes, well, in many cases there isn't any. Usually it's outdated even if it does exist, and sometimes it's just plain poor. And then of course we have this issue again of this dependency hell that we keep having to go back and cycle through the same issues. So here's an example of a piece of software that fulfills all of the conditions on the previous page. So this is this is the weather research and forecasting model. So it's WARF. It's one of the top 5 applications on Blue Waters. And it has about a dozen dependencies. So, well, it's not quite a dependency hell, but it's quite a few dependencies. The known issues in the last release are only documented on the website. They don't actually provide any patches for it. And they infrequently release bug fixes. They like to use an interactive configure script, and then even the result of that configuration script needs work in the end. You have to fix hard-coded paths, and you have to tweak some of the options as well. They use a custom compile script that they develop themselves that wraps around make. So basically, building a part that is broken unless you actually go in and fix the makefile itself. And then they don't have an installation step either. So really, wouldn't it be great if we could just install it with a single command rather than having to go through days or weeks of work to try and get it in there? And then that's where people in Ghent realize that this is a problem, right? And it's not just their problem, it's a problem that many HPC sites have. It's a huge burden on the teams because they're usually not familiar with these codes, so they have to understand their way around them and also the dependencies that they depend on. And it can take a lot of time to do that. And then researchers themselves, they waste a lot of time waiting for the support team to actually get the software installed. The sites in the past, the sites typically resorted back to in-house scripting. So they would do it, they would figure out a way of automating it, and they would do that for themselves. But it's not portable to other sites because of how different people use the system different systems differently. And of course, this is really a major issue because there was very little collaboration among HPC sites, even though everybody's having the same kind of a problem. And that's where EasyBuild came in. So the guys in Ghent realized that this is an issue, and one of them was thinking about how to go about solving this type of issue. And basically, it's a framework for installing software on HPC systems. It's just a collection of Python packages and modules. It was developed in-house in Ghent until 2009, and then they open sourced it. Since 2012. It's been through a couple of iterations since then. It's version 2 now. And the really nice thing about it is that the community is thriving. So it's been growing a lot in the last couple of years. There's a lot of people actively contributing, and those people in turn are driving the development in different directions, right, to make it more flexible and more comprehensive in what it can do. We have new releases every 6 to 8 weeks, and the last one was roughly a month ago. At the moment, it supports about 850 different software packages, including a lot that are pretty complicated to build if you're doing it yourself. CP2K, GrowMax, NAMD, OpenFOAM, That's a real nightmare if you ever tried to build that yourself. You'll know all about it. And the software itself is well documented, okay? So they put a lot of effort into creating the documentation platform for it as well. So just to give you an idea of the basic features that it has, it's a fully autonomous build system. So basically you run a command and let it go. It'll automatically resolve the dependencies for you, like your package manager might do. And it automatically generates the module files at the end. So basically you go from just a single command, you'll get the software installed, and it will also build the module file that you need for your users to actually access that software. It does a thorough logging of everything that it does during its build and install process. It'll archive the build specifications, so in EasyBuild language these are called easy configs. So it always creates an archive of whatever you've installed. It's very configurable. There are a ton of options for it, and you can use those via config files, or you can do them through the environments like we do in Jülich, or you can do them through the command line directly. It's dynamically extendable, so you can add your own additions in there for your own easy blocks, which is another word I'll explain in a minute, and tool chains. It also supports custom naming schemes. So for example, in Jülich we use a hierarchical naming scheme, and I'll talk a little bit about our own system at the end of the talk. But basically you can name your modules any way that you prefer. That's up to you. You're capable of editing that yourself. It's been comprehensively tested. There's a lot of unit tests in there, and if you ever make a PR against it, you realize that they push these things on you quite a bit, which is extra work, but it's obviously always a good idea. And there's a regression test as well before every release. It's actively developed, like we said, so which means there's a collaboration between a lot of HPC sites, and indeed, even with people in this room through EasyBuild, I've got to know a lot of people at different HPC sites exactly because we collaborate on this tool. And now these days it's a worldwide community, so it's also in the US and in New Zealand and Australia and Cuba actually recently as well. So just to give you an idea of some of the terminology that kind of came up in the last slide. So what we have at the core is the framework, which is basically the workhorse for the entire process. It's a set of Python packages and modules, and it provides all the functionality for the other pieces of EasyBuild. So it does all the grunt work for the building and installing. On top of that then we have EasyBlocks, which are just a Python module, which are a plugin for the framework. And basically what they are is a description of how to install, perhaps in a generic way, if you had something like a configure, make, install, or more specifically, if you have something that's very, well, like Wharf, for example, you need to do things in a very specific way, so you have a specific easy block for Wharf. And then you have an easy config file. So an easy block is for a piece of software, not for a particular version of that software, but for that particular software. And all the intricacies of what you need to do for a particular version or with a particular compiler, you hide that inside the easy block. And then in the easy config, which is supposed to be a simple file, you just have the specification where you say, I want this software with this version and with this compiler toolchain. So what we mean by a toolchain is a compiler with some accompanying libraries. So basically you build them from the ground up. On the base you would have a compiler, and then you would put an MPI implementation on top of that, and that would be a toolchain when you couple the two of those. And then if you include math libraries on top, that's also a toolchain. So that's another extension, and you build them in a stack like this. And so if you put all those three things together, the framework then leverages EasyBlocks to automatically build and install software using a particular compiler toolchain. And you specify those in an easy config file. So what does it actually need to run? It's more or less been developed for cluster systems. So the main target platform is really Red Hat based systems. So Scientific Linux and Red Hat and Santos. But it does work on other Linux distros as well, and people are trying it out on more and more systems. It kind of works on Mac, but that's not really a target platform. There's no Windows support, and we don't really plan to do that for the time being. It does have support on Cray systems. This is stable since the last release a month ago. And there's also support for power systems as well. Some people are using it on the Blue Gene Q over in the US, but that probably wouldn't be considered stable at this stage. It requires Python 2. It's not Python 3 compatible yet, but some people are working on it. It needs a modules tool, so you need to make a choice as regard what you want from modules tool, but it supports basically everything that's out there. Particular C modules, the tickle-only one that they used to use in Dyson at the beginning in Praise, and the one we would actually recommend is LMOD. If you're starting from scratch, you should probably use LMOD. And then of course you need a compiler to compile software, so you need to start from some kind of compiler. So if you're interested in just a quick demo of what a command line would look like to EasyBuild, there's the command itself, which is just EB. And then we have an easy config file. This is the typical name that you get, at least the name that it gets when it gets put into our repository. So basically, you got the software that you want, which is HPL in this case. You got the version of that software, and then you've got the tool chain that you want to build it in, and the version of that tool chain. And then the robot on the end is basically telling it to resolve all the dependencies, and if necessary, build those dependencies. So the first thing it will do is download any required sources. It does this by a best effort. If you can't download it freely online, then it won't be able to do that. But it will do its best. And if you need to get the source manually, you just need to put it in either in your current directory or in another shared location, and it will pick it up. And then the first thing it will do, if it's not already available, is it will actually build the tool chain. So the FOSS tool chain in this case is GCC. So FOSS stands for Free and Open Source Software. And so that's built up of GCC, and on top of that then you have an MPI implementation, OpenMPI, and then you have the math libraries, so LabPack, OpenBLAS, FFTW and ScalaPack, and they all couple together to more or less match up with the MKL. And so that's what we consider to be the FOSS toolchain. The 216A version, well, I mean, in general this is intended for cluster systems, so the OpenMPI implementation has a requirement that libIV verbs is available. You can of course define OpenMPI to not need that, but then you might not want to use it on your cluster. Basically, so it will build all that, and then once that's prepared and available, it'll build the HPL version, what you want on top of it. And it'll generate module files for each piece of that software along the way. So here's an example of what the output from an EasyBuild command looks like. This is basically just for GCC, but it goes through a number of steps, tells you when it's completed, and it'll also tell you that there's a log file available, and you can look at exactly what happened at each stage of the installation process. Just to walk you through what these steps are, and basically it breaks it down into, well, this used to be a lot smaller, but as more and more people get involved, more and more steps got introduced. But obviously the first thing is that it has to actually parse the easy config file, and then the next thing it needs to do is pull down the necessary sources so we can install the software. It'll check its readiness, so basically that means it'll look at the environment that you have and see if any changes need to be made for the installation process. The first thing it'll do is unpack the sources, and then if there are any patches, if you've defined that it needs to use any patches, it'll apply those patches. It'll do a preparation step, which is basically make any more changes to the environment that it needs for the configuration process. It does the configure. Once the configure is done, it'll build. If you've defined any tests for the software, it'll do them at this stage. If the tests pass then, or if they're done at all, it'll be installed. So sometimes then you might want extensions on top of the software. For example, if you're installing Python, you might want a whole set of Python modules on top of it. So these would be considered extensions, and they would be done at this stage. Once that's done, it will do a sanity check. So, I mean, in the easy block you decide what the sanity check is, but typically it's to see if a certain file or folder exists in the right place. Once that passes, it'll do a cleanup of everything it's done during the build process. Then it will create the module. If it will make any changes to the permissions of the installation if that's required. It also does packaging, so basically if you want to package the installation into an RPM, it can do that for you too. And then it'll run, at the very end, it'll run any test cases that you've defined. And all of these steps can be customized, some of them through easy config parameters, and some of them you might have to define your own custom easy block. It really depends. A lot of software can be done through some of the generic examples that we have already inside EasyBuild. What you need to be careful of is what EasyBuild is not. So it's not a build tool. It's kind of it's not a replacement for your package manager. and it's certainly not a magic solution to all your problems regarding installations. It is, or it can be, and hopefully it already is, a good way of installing scientific software. So it wraps around whatever scientists choose to do within their own build processes. It provides a uniform interface that wraps around these procedures. It can save HPC sites a lot of time, particularly because it's collaboration, right? If other people have done all the work on OpenFOAM, you don't have to, right? So that's a lot of time saved, both for your user, your end user, and the team itself. And it automates all these tedious and repetitive tasks and keeps nice logs of everything that you can view after the fact. And what I personally like about it is that it provides a consistent view of software to your users. So things are installed in a consistent way, and they know if they move from, well, we have multiple clusters. If they move from this cluster to that cluster, things in general will look the same, will be installed in the same way. So they know that if something worked here, then more than likely it should work similar on the other system. Yeah, maybe it's considered an expert system for software installation. It depends on how you view that. If the people who are experts are the ones who are installing software system-wide, then yeah, for sure. But it's also going to be used by a general user. It does not necessarily just for the HPC support teams. It's a platform for collaboration, and that's one of the reasons I really like it, is because it gives us access to people from other HPC sites, and we can work on similar problems. We have a Blue Gene queue at Jülich, and somebody in the US has done an awful lot of work on porting, on bringing the IBM compilers in the Blue Gene queue being supported within EasyBuild. They've done that work, so I don't have to, but I can help him to make that work better, because I can provide a different system for him to do things on. And then of course, yeah, it's a tool to empower users that they can actually think about managing their own software stack completely, if you were so inclined. Sometimes we wouldn't probably encourage that. But, so who exactly are the community? There's the main developers, who are all housed in Ghent, and more specifically, and they're partners in this Flemish supercomputing center. There's ourselves in Jülich, and we're some of the big sites, so CSCS is another one of those big sites. There's a lot of small sites all across Europe. There's some sites in the US, and across the world, New Zealand, Australia, and Cuba as well, and probably more. And there are some commercial companies who use it as well. There are some we can mention, like Bayer. There are some that we can't mention, and that maybe I don't know, but the developers do. And then there are all the people who are silently using EasyBuild and haven't raised their head out of the water yet. Because probably there's a lot. It's open source, it's freely available, and the community is getting bigger and bigger. How much time? So just by the numbers, what's been happening in the community over the last while. So we've had 6 sessions at ISC and SC for getting scientific software installed, birds of a feather sessions. We've had 10 hackathons to date, and this year was our first user meeting, so that was held in Ghent back at the end of January. And there's about 20 or 25 people on the IRC channel that we have. There's a couple of dozen sites using it. We've had 47 conference calls. The number of people on the mailing list is consistently growing, so we're up past 160 at this stage. In terms of the contributors back to EasyBuild, it depends on where you look, how many there are. So the easy configs are the easiest thing to contribute back, and obviously that number is growing steadily. We still get growth on the other 2 as well, but they're a little bit more involved. To write an easy block takes a little bit more effort, and for the framework that's even more true, because you need to understand what's going on underneath the hood. But still these numbers are pretty high as well, for unique contributions. There are alternatives out there, and so one of the major ones is probably SPAC, which is in Lawrence Livermore. There are a couple others as well, Mali and Smithy. I don't know these tools personally so well, but the other guys in EasyBuild do a little bit more. From what I understand, they take a different approach. Pretty sure that they have a smaller user community than we do. They definitely support less packages than we do, so we're pretty proliferative as regards packages. They might have less features than we do, and maybe they're less flexible than we are. And most of them are not as powerful, except perhaps for SPAC. So SPAC's been, a lot of work's been put into SPAC. But there is, all of them have talked about doing some cross-community collaboration, so trying to see if we can work together And one of the main developers, Kenneth, told me last week that he really thinks that having SPAC side by side with EasyBuild is probably a good idea, and we're going to work towards seeing how we can make that happen in an easy way. In terms of future work that we're looking at the moment, well, obviously we want to support more software. That would be high on our list, and that's probably a never-ending story. Documentation is good, but it could be better. We need to explain more about the generic easy blocks that we have, which are the ones that people will probably use the most. And maybe more about the API for the easy blocks themselves and how you can write your own. We want to do some specific stuff for LMOD too. So LMOD has features that would be nice to leverage that we would also like to do. What we would like to do is make the support for sub-tool chains a bit more robust. So that's something that I implemented. But basically, when I described tool chains, I said how they're basically stacked in the sense that you have a compiler, and on top of that you have an MPI, and on top of that layer you might have a math library. And so basically, you should be able to search down through the entire stack. And that before this year, that wasn't really possible, but now it is. So that should make the number of necessary easy configs a lot less. We want to have better integration with GitHub so that the process of contributing back is a lot easier. We would like to do RPath style linking. I mean, more or less the code to do that is inside, but the testing is the thing that's lacking. We were also thinking about a kind of a fat easy config format. So rather than just have a single version of software in a file, we might be able to support a fat file that can have descriptions of multiple versions. And then this idea of maybe joining forces with SPAC somehow, so trying to work together a bit more. And if you want to know more, I think these slides are all online, so you can take a look through here. And there's all the various things, various links, so you can get involved or see what people are doing. So I just wanted to cover, do I have time or am I out?
5 minutes.
Okay, so
questions,
yeah. Well, I just very quickly walk through exactly how we use things a little bit. So we have a big cluster system in Jülich, and I actually manage the software on that. It's a 2 petaflop system, and it also has GPUs inside. What we provide to the users is a hierarchical view. So basically that means when somebody logs in, the first thing they have to do is load a compiler. When they load a compiler, they see all the software that's been compiled with that compiler. And in there are the MPI implementations. So they choose a particular MPI implementation, and once they've chosen that, they'll see all the software that was compiled with that MPI implementation on top. And that's the general user view that we have. Why do we choose a hierarchy, and why do we use LMOD? The problem for us, because we have this architecture that includes GPUs and everything, we have to support multiple compilers. So we have GCC, we've got the Intel compilers, and we've got PGI. And then we have a lot of different MPI versions that we have to support. Intel, we've got 2 versions of a Power Station MPI, it's called, the non-threaded and the threaded versions. And then we have a GPU-aware version, GPU-aware MPI as well. There are 4 MPI implementations. And for us, that's a module explosion, right? How do you differentiate between them? So the hierarchy was really to simplify the naming and the user view, so how people see things. And then we also wanted to enforce some consistency, that people don't mix and match software from different tool chains. And the reason we chose LMOD is because Tickle module is not really developed anymore, and the feature set's very limited, and there's some bugs in there that may not ever get fixed. So we chose LMOD because it's faster, it has a cache, it uses a cache, it doesn't keep doing things at runtime only. It also has a way of searching, so that's a module spider. It supports hidden modules, and then there's these additional features that can be very interesting depending on your use case. So this is the user view that I showed you, but actually things are a little bit more complex than that. What we have at any point in time is a production view that an ordinary user would see. But if people want, they can take a step back and they can look at the entire extended view. And actually what we do is we implement a new stage every 6 months. And then we will actually change that user view automatically after 6 months, which basically means that it allows us to retire all compilers or all software and just move the view forward. So basically we get new projects every 6 months, and the idea is to couple that with a change of the software stack every 6 months. But if somebody still wants to go back and use a version of a particular software from 2015, they can do that just by taking a step backwards and going into the extended view and loading this particular stage and all the work. I mean, so if you want to turn around and install OpenFOAM, EasyBuild can do that for you in a single command. If you want to integrate a new piece of software that's very difficult to integrate, that will take time, and yes, there's a learning curve involved. failed builds have to be restarted from scratch. That's true. And if you're building open foam and it takes hours to build open foam and you have to start again from the beginning, that's very frustrating. But it's like a necessary evil because you want to ensure that you can go from the beginning to the end without having an error. And then they will say, oh, but my particular software, it doesn't fit the model for this or that reason. Basically, if you can type commands into your computer that result in the piece of software being installed, it fits the model. You just need to figure out how, and well, we help them to do that. The other thing that we get that's specific to us is that there's no place for static installations within our stages approach. That's not really true because you can always take that step backwards into the extended view and always find old software. What about long-term software support? The answer is the same. The issue that we've really had is that the responsibility for software has come back onto the people who know the most about EasyBuild. So people just turn around and go, oh, this is so much easier for you to do than for me, so maybe you should. And that's something that I'm trying to fix within our group, so to try and distribute the knowledge about EasyBuild a bit more. What have we contributed back? So we've done things that maybe are not so important right here now. So we've done things like a core GCC underneath everything, which is like a system compiler, minimal tool chains. We've implemented things so that you can change your naming scheme on the fly. You can configure the default optimization, and then we've contributed hierarchical naming scheme and bug fixes as well. What do we worry about? That the environment will explode. So we're so successful in installing software that we now have hundreds of packages, right? And these days, if you even load Python, it turns out that way down in TK, Python depends actually on X11, right? So if you really want to go all the way down, then you should also be installing X11 when you're installing Python. So actually the list of dependencies is actually huge. So I'm worried about the environment getting too big for people, and that's why we think about our path these days. The dependencies in the module view create clutter. That's why we want to hide dependencies typically, so we only show people what we think they actually want to see. And then we want to minimize the versions. That's why we have our stages approach, so we don't have many versions of the same software around. And then, well, more we worry about GPU-enabled software, so we want to support more GPU packages. And then because we have so much software installed, there's a lot of inodes, and sometimes that causes us problems too. I think that's it.
Okay.
Sorry.
Thank you.